Hi, let's talk about the limits that all optical systems, including your eyes, have to finding out and seeing very small objects. And that limit is called the Rayleigh limit, which is an application of circular diffraction. So with Fraunhofer diffraction, when waves hit a narrow opening like this or like this, you get a spreading of the wave in a direction that happens to be perpendicular to the feature that they've encountered. So for openings like this, you see a spreading along the horizon. Well, if you hit a circular opening, then what you end up seeing is a bullseye pattern with a center bright spot and then a dark ring, then a bright ring, then a dark ring, then a bright ring, then a dark ring, and so on until you just get too faint for you to be able to detect that pattern. Now, to figure out the spacing of all of the rings involves using some differential equations that are well beyond the scope of our physics class. But there's a simplish solution for looking at the first ring. And what we end up seeing is the angular separation from the very center of the bullseye to the center of the first dark ring occurs at the sine of an angle that's equal to a factor of 1.22 times the wavelength of our wave divided by the diameter of our aperture. Now, with the Rayleigh limit, if 2 points of light happen to be within that angular limit, they're going to blend together. So for an example of that, imagine a car driving towards you on an incredibly long, flat stretch of road. So if it's far enough away and it has two headlights, those two headlights might appear as if they're just a single point of light from far away. But as you start getting closer, it starts to look almost like this kind of barbell double point. And then at some point, you start seeing those lights separate, and from there on, you're really clearly seeing two individual light sources. Well, the limit is hit when the center of the bullseye pattern from one point of light is in the first minimum of the bullseye pattern from its neighboring point of light. And that's when you see that sort of double barbell, or if you have done a lot of astronomy, looked at stars through a telescope, you sometimes see double stars. Same idea. Telescopes, they have a diameter. That diameter sets the limit that you can see, which is why most telescopes have huge diameter mirrors or really big lenses if it's a refracting telescope and not a reflecting telescope. It's all about trying to help with the Rayleigh limit. There are other ways that we can work with the Rayleigh limit, because sometimes when we're dealing with things like microscopes have pretty fixed diameter apertures. Your eyes don't have a very wide range of diameter, if you think about it, for how large your pupil can open. So there's only so much we can do with increasing the diameter in some cases. One of the other things we can do is change the frequency of light, because the higher the frequency, the shorter the wavelength. So a lot of microscopes will use the near ultraviolet for imaging because that shorter wavelength gives them a smaller, resolvable sized feature. And you could also make use of refraction effects. The index of refraction not only adjusts the speed of light in a material, it sets the wavelength of a light wave in that material. And the wavelength of light in a material is the wavelength in a vacuum divided by the index of refraction of that material. So a lot of slides will use an oil layer between the object you're trying to image and the objective lens. The whole job of that oil layer, it has a higher index of refraction than air, shortens the wavelength of light on its own, giving you that little bit more detail than what you could get from just using air between your microscope and what you're trying to see. So let's take a look at something that we might want to take a look at. If you're really into insects, there's an insect called a tiger beetle, and it has little tiny colored patches all over the wings of its carapace, and the size of those individual patches is about 1.72 microns, which is pretty tiny. Now, just for context on size, if you are reading a textbook, the period at the end of a sentence in a printed textbook is usually somewhere around 100 microns. So this is 60 times smaller than the period at the end of a sentence. Now, on average, visible light has a wavelength in air of about 550 nanometers. And the human eye's pupil can vary in size, so if you were to pretty extensively dilate your eye, you could get a diameter of several millimeters, not meters. You're not getting a pupil that large without doing some serious damage. So let's say that the diameter of your pupil happens to be 3.90 millimeters. So the smallest angle that you could see would be proportional to the size of the feature that we want to see divided by the distance we are away from that object. And by Rayleigh's limit, that would be equal to 1.22 times the wavelength of our light divided by the diameter of our pupils. So the distance we need to get would be equal to the size of the feature we're trying to see times the diameter of our pupils divided by 1.22 and the wavelength of light. So if I plug in the size of my feature, the diameter of my pupil, millimeters, 10 to the negative 3 meters, 1.22, and 5.5 times 10 to the minus 7 meters, 550 nanometers, we get a distance of 1 centimeter away, which even if you're really cool with bugs, there's a big problem because the human eye has a near point to its vision. And even for folks that are horribly nearsighted, that near point is still usually beyond 5 centimeters away. So there is a smallest feature you can see. Professors, when we are trying to be smart, try to be very careful about that and think about your eyes, think about the size of any optics that we're working with, and we can make things that are too small to be seen in a classroom, too small to be seen on a camera, and architects, really something to start thinking about when you look at better designs. Having a really deep, really sort of far away, narrow lecture hall isn't great for a lot of reasons. Most of which the folks in the back can't see what's going on. Thanks for watching.